Welcome to yet another TCS Plus talk. Today we have Shachar Lovett from UC San Diego, who is going to talk about log rank conjecture and communication complexity and his recent progress on that towards resolving the conjecture. Shachar did his PhD from Weizmann and then was at the Institute for Advanced Study, and since last year he has been a faculty at UC San Diego. Apart from that, the next two talks are by Nikhil Srivastava, which is in 2 weeks from now, and then Lorenzo Vecchia from 4 weeks from now. And during the talk, as usual, we'll have the mics muted. And if you have a question, you should interrupt the speaker. You're encouraged to interrupt the speaker. And now we'll go around the table to introduce the groups one by one. So, well, first, Thomas Hollenstein is there from ETH Zurich, who is operating, and then I'm here at the Simons Institute at Berkeley. Then we have the group at Simons Institute. Then we have a group from ETH Zurich. Then we have a group from Columbia.
Hi.
Then we have a group from Brown. Then we have Yop and Aded, and we have a lot of big group from NYU. I'm assuming there are lots of people. Then we have a group from Aarhus in Denmark. The group from TTI Chicago and U Chicago.
There is 5 of us.
And final talk.
Yeah, I think we should start. I may have muted Shachar by mistake, so Shachar, you may have to unmute yourself.
Okay. So can you hear me?
Yes.
Yes, good. So thank you for inviting me to speak in this seminar. It's a great seminar series. So, and okay, should I start?
Yes.
Yes. Okay. Good. So what I'm going to be talking about is about some recent progress on the log-rank conjecture, and okay. So let's see. So just to recall the usual setup. So in communication complexity, we have two parties, Alice and Bob, and each of them have a part of the input. Each of them have their own input, and they wish to compute some function of the joint inputs. So this is sort of the simplest setup of communication complexity, because we only have two players. You can think of having more players and having some shared inputs between them. So, but we'll really be focusing on the simplest model, and which would be, two players, deterministic protocols, and Boolean functions. So the function that they compute. So Alice holds x and Bob holds y, and they want to compute some Boolean function of x and y. And sort of the question is, okay, so how many bits do they need to exchange between them to solve this problem? So this is a basic setup of communication complexity. And again, if you just look on deterministic protocols, then there is actually a very simple, very nice lower bound which comes from what's called the log-rank lower bound. So let me explain it. I'm sure most of you know it. So we can envision our function as a matrix. So x indexes rows in the matrix and y indexes columns in the matrix. You can think of the player as one being the row player and the other being the column player. So the row player knows the row of the matrix, the column player knows the column, and together they want to discover what entry lie in the intersection of the row and the column. So we identify a function with the matrix, and I'm using plus and minus to denote +1 and -1, just for shorthand. And sort of, what is a deterministic protocol? Well, a deterministic protocol is just a way to partition this matrix to rectangles which are monochromatic. So let me explain it by an example. So let's say the row player first sends the first bit. So the first bit is either 0 or 1. So it corresponds to partitioning his input, meaning the rows, to the rows under which he would send 0, and the rows under which he would send 1. So it's some partition of the rows. So that was the first bit sent. Now the second bit sent is now by the column players, and it could depend on what's the answer that the row player sends. So it gives it a final partition. And then the row player sends another bit, And actually now we're done, because given these 3 bits, we got a partition of our matrix to rectangles, and each rectangle is either all of it +1 or all of it is -1. So this is called the monochromatic rectangle. And sort of a protocol is more or less equivalent to a way of partitioning a Boolean matrix to a small number of monochromatic rectangles. And if you have a protocol that's using C bits, it corresponds to partition to 2 to the C rectangles. Okay. So this gives the first lower bound in communication complexity by Mehl and Schmidt from 82, which goes as follows. Well, if our function has a C-bit protocol, then the matrix can be partitioned to 2 to the C monochromatic rectangles. But this actually gives a bound on the rank of the matrix, because each monochromatic rectangle has rank 1. It's a rank 1 matrix, and if you add 2 to the C of them, you get rank of at most 2 to the C. So meaning if the rank of this matrix is large, then you have to send many bits to compute it deterministically. So the log on base 2 of the rank over the reals of this matrix, or I must denote it by rank of the function, sorry, of the matrix, gives a lower bound for the deterministic communication complexity of any function. And this was again one of the earliest lower bound techniques in communication complexity. And the question is, okay, how tight is it? And what might be surprising is that in all the known examples, it is tight up to polynomial factor. So it's not exactly tight. There is some polynomial slackness, but up to polynomial factors, it is. In all the examples that we know, this is tight. So sort of this motivated the conjecture of Lovett and Sachs from 88, which is called the log-rank conjecture, which speculates that this simple lower bound of log of the rank is actually an upper bound up to polynomial factors, or equivalently put, for every Boolean function, its deterministic communication complexity is at most polynomial in the log of the rank. Okay, so this is a question that will be studied, like trying to attack this conjecture. Now, but you should know that this conjecture actually came up in different other frameworks. They all are asking about the same mathematical question, but they give it different interpretations. So in graph theory, it was already asked in the 70s, and then again in the 80s by Nuffel and Lewitz, hopefully I said it right, about the relation between the rank of the adjacency matrix of a graph and the chromatic number of a graph. And the same question you can ask about the relation between the notion of a rank and positive rank for Boolean matrices by Anakakis. So, but all these questions are actually asking the same mathematical question in different customs. So we'll be talking about the log-rank conjectures in the communication complexity framework. So what has been the progress up until now? Well, first of all, you should notice there's a very simple upper bound on the deterministic communication complexity, which is just a rank. So remember, we tried to prove something related to the log of the rank, but if you increase it by an exponential, the rank of the matrix is always an upper bound, because if a Boolean function has rank R, it can have at most 2 to the R distinct rows. And hence, you can assume all the rows are distinct, or if 2 inputs for the row pair give you the same output no matter what, you can identify them. So you can just send the index of a row. So there's always a trivial upper bound of rank, and this was improved to something linear. So the best was work by Kotlov, following work with Kotlov and Novash, given something like 0.4 times the rank. And in terms of lower bound, so initial conjectures in graph theory were actually that the log of the rank is actually the right bound for the chromatic number of a graph. But it turns out this is not the case, so there were better and better lower bounds discovered. And the best one is by Kushilevitz from 94, given an example of functions where the deterministic communication complexity is at least the log of the rank to some power roughly 1.6. So, for all that we know, maybe log rank squared is an upper bound. And last year, in a joint work with Eli Ben-Sasson and Noga Ron Tzvi, we showed that if we assume a number theoretic conjecture called the polynomial Feynman-Ruscha conjecture, then we can improve the upper bound by a logarithmic factor to rank over log rank. So this number theoretic conjecture is relatively widely believed to be true, and it's proved under some weaker bounds, but nevertheless, this is a conditional result. Okay, so this was the progress before the work I'm going to tell you about. And what I want to tell you about is a new technique to bound, which gives an upper bound of roughly roots rank to the deterministic communication complexity. So I'm going to describe how this proof goes. But I just want to make note that this doesn't assume any conjecture, so this is unconditional. So what is the main ideas of the proof? So what I'm going to describe from now, for most of the talk, is just how do we prove it, and then I want to talk a little bit about some relations to extensions of it, to other problems in communication complexity, and to problems in matrix rigidity. So basically, there is a classic result of Nissan and Wigderson that shows that if you want to build protocols, it's actually enough to find one large monochromatic rectangle and recurse. So that's the first step. So just a reduction that it's enough to find large monochromatic rectangles. Okay, so that makes our life easier. And then we're going to start with a technique that was widely used to prove lower bounds in communication complexity, which is called the discrepancy method. But we're going to view it, we're going to flip it. So instead of viewing it as a way of proving lower bounds, we're going to view it as a way of proving upper bounds. So it will give us that there's always a large rectangle which is slightly biased. It's not half plus 1, half minus 1. It's slightly biased, let's say, towards the plus 1, more than the minus 1. Then we're going to use amplification to give rectangles which are very, very biased. Almost all of them are going to be plus 1. And then we're going to combine this with the low rank property again to show that we have large monochromatic rectangles. So that's the basic ideas in the proof, and now we're going to go over them one by one. So the first step is how do we get deterministic protocols from large monochromatic rectangles, which was proved by Nissan and Wigderson. So again, so what's the main idea here? So the log rank conjecture speculates that we can partition any low rank Boolean matrix to a small number of monochromatic rectangles. In particularly, any Boolean matrix of low rank should have a large monochromatic rectangle. So this is a necessary condition, and what Nissan and Wigderson show that this is also sufficient. So let's see the proof idea. So let's assume that any low rank Boolean matrix, we have some way of showing that it has a large monochromatic rectangle. So here is our matrix. It's an n by n matrix, and here is our rectangle. So let's partition the remaining parts to 3 blocks. Let's call them A, B, and C. So we know that our matrix has rank R, and we know that this monochromatic rectangle has rank 1, because it's either all plus 1 or all minus 1. So it means that the rank of A plus the rank of B is at most R plus 1, if this entire matrix has rank R. So one of them should have relatively low rank. Let's say A has rank roughly R over 2. It means that now, well, the row player can send 1 bit and partition the matrix to 2 halves, to the top half and the bottom half. And then we're going to recurse. And sort of the top half, the rank is going to improve by a lot. The rank is going to go to roughly R over 2. The bottom half, well, the rank might stay the same, but it's going to be a smaller matrix. And if you recurse, then you get the bounds. So basically what we're going to show, that the main technical theory is going to be the following. Any n by n Boolean matrix with rank R has a monochromatic rectangle whose size is n squared, so the matrix times that is exponentially small in roughly roots rank, up to some logarithmic factors. So this means that this exponential really is a fraction of the monochromatic rectangle inside the entire matrix. And by the Nissan-Wigderson result, this translates by using this again to a protocol which uses root R times log R many bits. So are there any questions up until now? So the main thing we're going to show is that any large Boolean matrix which is low rank has a large monochromatic rectangle, and large quantity is stated here.
So this cannot be the tightest possible bound, right? Because if R becomes very large, then this gives something trivial. You would expect this number to then go to 1 or something, like n squared times x bin minus root R. If R tends to n, this should become 1, but this becomes much smaller than 1. So
Yes, so but the log rank would require to prove something quasi-polynomial in R.
Okay.
This would be the conjecture, but we don't know how to show it.
Okay.
Yeah. All I'm saying is that finding a large monochromatic rectangle is essentially equivalent to building a protocol. Any other questions? Okay, I'll continue. So that's going to be our goal for now. So the next thing I want to describe is this technique called discrepancy, which was in particularly used in these two works, but in general it's a very useful technique for proving lower bounds in more general settings. For example, if you have randomized protocols or quantum protocols and so on. So discrepancy turned out to be a very useful technique for lower bounds, but we're actually going to use it to actually build protocols. So let me define the notion of a discrepancy. So again, we have an n by n Boolean matrix. Let mu be any distribution on the elements of this matrix. And the discrepancy of the function with respect to this distribution is just the maximal correlation that f has with a rectangle. So what does it mean? We're maximizing over all xy subset of n. So x times y is go over all possible rectangles. And what we're asking is, inside this rectangle, what is the average of f with respect to the distribution mu? Right? So notice that we're not conditioning mu to be inside the rectangle R, we're deleting all the other parts outside R. So this is the definition of a discrepancy. So basically we're asking what is the largest correlation our function has with a nice function, like a rectangle. And basically, a basic theorem here is that low-rank functions have a noticeable discrepancy. So for any distribution mu, you can find a rectangle such as the discrepancy of f with this distribution mu is going to be at least one of the roots of rank. Or no, otherwise put in words, set in words, for any distribution, you can always find a large rectangle that has correlation 1 over root r with the function. And sort of the proof of it really uses the fact that you're doing everything here over the reals. So it uses, so there are two ways of proving it. One uses John's ellipsoid theorem and to argue about it. The other one builds as an SDP, look on the dual SDP, and then again uses notions, uses the fact that you're working over the reals. And this bound of 1 over root r, you might think is it tight or not, and it's tight. So in general, it's tight. So if you take the Hadamard matrix, the n by n Hadamard matrix, then its discrepancy is really 1 over root n. So its rank is full, and its discrepancy is 1 over root n. So we don't really hope of improving this bound in general, just assuming low rank. There might be ways of improving it, assuming that you have low rank and large matrices, maybe. But if you just look at the rank, if you just look at this one parameter, then that's the best you can hope for. Okay? So now the question is, how are we going to utilize this? And this is going to be in our step 3, which is amplification. So here's our function initially. Let's say it's unbiased. It's half plus 1, half minus 1. It looks random. And sort of by this discrepancy, we know that we can find a rectangle where our function is slightly biased. It slightly tends more towards plus 1 than towards minus 1. And then we're going to find another rectangle which is even slightly more biased, and another one that's even slightly more biased, and we're going to continue until our function is going to be super biased. And sort of, so that's the main idea. And sort of, sorry, what's going to be crucial here is that we can choose the direction in which we're going to use a bias. So we can always choose, for example, to have more plus 1s than minus 1s. That's going to be an important step, important part. So let me go over the details. So we have a function that has rank r, and let's assume for simplicity initially that the function is unbiased. So the average of the function is 0. And I'm going to use the following notation. The average of the function on a rectangle, well, just what you think it should be. It's just the average or the bias of the function on a rectangle R. So maybe the function is unbiased if you look at the entire space, but if you restrict to a rectangle, maybe now it becomes somewhat biased. And sort of discrepancy, if you plug in the uniform distribution as your input distribution, tells you can always find a large rectangle on which your function is slightly biased. It tends toward either plus 1 or minus 1, more, with the fraction of roughly 1 over root rank. So this is going to be the property that we want to try and utilize. And what's going to be important, I'm going to stress this in the next slide, that we can choose the sign actually. We can choose whether this bias is going to be positive or negative. So let's see why. So let's say here is a function, its average is 0. And all that we know how to prove from discrepancy is that there is one rectangle R on which our function is biased. It tends to either plus or minus, which like average 1 over root R. But it means if we complement this rectangle to the 4 other rectangles, so we have R, R prime, R double prime, and R 3 primes, because the average of the function overall is 0, on one of these rectangles, it must be positive and biased. So maybe we use a factor of 3 here, but on one of these rectangles, the average of f has to be at least something like 1 over root R, or 1 over 3 root R. So this is going to be important for us, so let's see why. So let's assume in general that we want to do the simplification step, and we are at some intermediate point. So we have some average C, which let's assume for simplicity it's non-negative. Now we're going to choose our distribution carefully. So we're going to choose a distribution under which the function is going to be unbiased. So the function is going to be plus 1. So the distribution is going to be of giving half the weight to all the plus 1 elements and half the weights to all the minus 1 elements. So because the average is C, we have more plus 1s than minus 1. So this is going to be, it's not going to be the uniform distribution anymore. It's going to be a sub-biased distribution, giving more weight to the minus 1 and less weight to the plus 1. And third of that, but important is under this distribution, f is unbiased. This is just the way we chose it. So we can apply the discrepancy and the fact we can choose the sign again, and say we can find a rectangle under which our function is going to be biased and end with a positive bias. And when you combine these things together, what you get is that if you started with an average C and you apply this bias amplification, you get a large rectangle under which the function has a larger bias, well, it's the original C, plus something like 1 over root R, except C if C is already very close to 1. So this is what you get from this amplification step. So because you can always find a large rectangle and guarantee that it's going to give you an advantage to the bias, increase the bias, and not decrease it, you don't really do a random walk in a way. You always move in the positive direction. So that's going to be important. So let's see what happens. So this is what you get from this amplification step. So sort of, if you want to analyze it, then you can think, well, if you make a root R, the first root R steps are going to get your bias to be something like 0.9. And then if you make another root R steps, now C is going to be very close to 1, so you're going to advance less, so it's going to be something like 0.99. You make another root R step, you're going to 0.999, and so on. And basically, if you want to get your bias to be very close to 1, like 1 minus epsilon, you need root R log 1 over epsilon steps. So basically, every root R steps, you get exponentially closer to 1. And sort of the question here, if you just stop here, is, okay, we get this protocol, but how do we get a monochromatic rectangle? Like this is only going to give us more and more biased rectangles, but it's never going to give us a fully monochromatic rectangle, because the only guarantee we can get here is that the average is going to be very close to 1, but not exactly 1. So to get an actual monochromatic rectangle, we need an additional step, which is going to use again the low rank property. So we already use a low rank property once to get the discrepancy bound. We're going to use it again to show that if epsilon is small enough, you can stop. You don't have to go all the way up to 1. So that's our first step. So here's the lemma. If a Boolean function has rank R, and its average is sufficiently close to 1, let's say 1 minus 1 over 4R, then it has a large monochromatic rectangle. Large is a constant fraction of the matrix. So this tells us that, in the amplification phase, we don't have to go all the way. We can stop when epsilon is 1 over 4R, then apply this lemma, and get a large monochromatic rectangle. And large here is, well, how large is large? Well, we needed to make roughly root R log R steps to get up to this epsilon, because every root R step, epsilon improves by a factor of 2, which using this Nielsen-Wigderson theorem means we can always find a protocol, we can find a monochromatic rectangle of size n squared exponential minus root R log R, which is going to give us a protocol using root R log R many bits. So now just to conclude, we need to prove this lemma, and the proof is going to be relatively simple. It's actually from a previous paper I had with Dima Gavinsky. So here is the rank and the average. So here's the proof. So I'm first going to explain by words, then by picture. So we see the function is super biased, so we can just delete. So think of the most rows are going to be almost all of them +1, and only few of them are going to be -1. Because we're assuming the average is so large that most of the entries are +1. So first, let's just delete the rows that have too many -1s. So maybe we deleted half the rows, and now we can assume each row has almost all of its elements are +1. Let's say n/2r. It has at most n/2r elements which are -1. Well, now because we have low rank, we can choose r rows that span the entire matrix. Right? Let's say the first r rows. Now just by union bound, in half of the columns, these r rows are all going to be +1, because in each row, almost all of the elements are +1. So we just restrict now to this element. Now we delete half the columns, and now you get all the rows are either +1 or -1. Choosing the larger half is going to give you this monochromatic rectangle. So at the end we lost the factor of 8. So showing by picture, so here's our matrix. Let's say it's spanned by the first 3 rows. So now each row I'm assuming have many +1s, so we deleted the ones that don't have many +1s. So because in the first 3 rows most of the elements are +1, we can find columns which all of them are +1, and because they span the entire matrix, if you look at the entire rows under these columns, all these rows are either all of them +1 or all of them -1, and then we just choose a larger half. In this case, we're going to have +1s. So that's the idea of this final lemma. So to summarize, so what we proved here, so the previous results give an upper bound of roughly rank over the log rank, and the lower bound which is polynomial is the log of the rank. And what we did here is improve the upper bound by roughly a quadratic factor to root of the rank. So there's still a long way to go up to pushing it down to polynomial log of the rank. So, but maybe there are going to be some ways of utilizing the ideas we developed here with some other techniques. And the proof idea used this following 4 steps. So first we use this classic result of Nissen and Vigdorson showing that it's actually sufficient to just find one large monochromatic rectangle. Then we use the discrepancy bounds to show that we can find a rectangle which is large and is slightly biased. Then we had an amplification step, which allowed us to go for a rectangle which is very, very biased. And finally, we combine this with the low rank property again to show a large monochromatic rectangle. So those are the main ideas of the proof. And now I want to talk about 2 open problems and a little bit of speculations. So first I want to tell you about a related question I'm interested in. It's actually a conjecture on low-rank sparse matrices, which I think actually captures what we're actually doing here. And so out of the roots, the rank is going to be the tight bound. And if it's true, it's going to give us improved bounds for matrix rigidity. So I'm going to explain this first, then I'm going to talk a little bit about extensions, potential extensions to more general protocols, for example, randomizer quantum protocols, and then some speculations. So first, I want to tell you about this conjecture. So I want to say that, well, while what we analyzed here was really about low-rank Boolean matrices, I think everything here should work also for low-rank sparse matrices. So think of sparse as being, half the elements are 0. So being half +1, half -1, by changing the rank by 1, you can assume half the elements are 0. So you're really in this setup. So let me tell you the conjecture. The conjecture is the following. If you give me an n by n matrix, real matrix, that has rank R, and let's say half the elements are 0, then it has a 0 rectangle, which is large. And large is n squared times exponentially small in roots the rank. And sort of here, this is a tight answer. So I'm going to show you soon why this is the tight answer, the tight result here. And sort of what I'm speculating, but I don't know how to show, is that there is a way of adapting the techniques that we developed here to prove this stronger. So this has half zeros and half other elements. It doesn't have to be +1. So that's sort of the generalization here. So here's the conjecture. So why are the bounds the best possible? So think of the following example. So let's just factor A to be x transpose, where x is an n by r matrix. So the rows of x are all the Boolean vectors of length r that have Hamming weight, let's say, root r over 10. So n is something like r to the root r. And So why is this tight? Well, on the one hand, this matrix is very biased. It has almost all of the elements are 0 because the probability that two vectors of length root r over 10 intersect is something 1 over 100. So this is, if 99% of this matrix is 0, but then if you want to ask what is the largest 0 sub-rectangle inside it, it corresponds to shooting the rows to be vectors supported in the first half of the coordinates, and the columns to be vectors supported in the last half of the coordinates. And you can work out the details and see this is going to be exponentially small in the root rank. So sort of if you just assume that you have a sparse matrix, in this case 99% of the elements are 0, we can't hope for anything better than exponentially small in the root rank. But why is this conjecture interesting? So let me tell you of a corollary of this conjecture, which is going to give us a slightly better bounds for matrix rigidity. So let's set the rank to be log squared. Then I'm going to show you a way of constructing a matrix. So actually the first row says it. So let A be an n by n matrix of rank R. So it's a low rank matrix, but in a very robust sense. So all the R by R minors have full rank. Okay, so R is a parameter. So all the R by R minors have full rank, but that's it. So the matrix has rank R. So you can actually generate this matrix by, let's say, choosing the rows and columns to be elements of length R which are linearly independent. Every R of them are linearly independent. So there are easy ways of constructing such matrices. And sort of the corollary with the conjecture would be that we can actually set the rank to be log squared n. So this will be a matrix of rank log squared n, but you cannot reduce the rank by changing the constant fraction of the elements. So sort of you can change half the elements of this matrix, and the rank is still going to be log squared n. And this beats, the best argument that we know for matrix rigidity, which only give you rank log n. So it improves by a log factor, and you can work out that this conjecture also for general parameters improves this untouched minor by a log factor. So it's a small improvement, but still, matrix rigidity is a hard problem in general. So what's the proof? The proof is going to be simple. So let's say we have a matrix that is an n by n matrix of rank R, and all of its R by R minors have full rank. And let's say that we can decompose it as a sparse matrix plus a low rank matrix. So this is a setup in matrix rigidity. So S is sparse, let's say it only has half non-zero elements, and L is low rank, it has rank lower than A. But then if you look at the sparse matrix, well, it's sparse, but it's also low rank, because it's a difference of a low rank matrix A with a low rank matrix L. So because S is both sparse and low rank, we can apply the conjecture and that S has a large zero rectangle. And so if this rectangle is larger than R by R, then, and our matrix A has to have rank R in all the R by R minors, then also L has. So L has rank R. So sort of, you can work out the parameters and see this gives you rank log squared L for matrix A. So this is one reason why I think this conjecture is interesting, but so far I don't know how to prove it, and if I encourage people to think about it. And sort of you can think about this conjecture over other domains, for example, over F2. So this was called the approximate duality conjecture by Eli and Noga. And there somehow you need to assume slightly more. You need to assume that the matrix is somewhat biased, let's say. And they had a different application for two source extractors. And there we know actually also very little how to prove the things. And sort of, but the geometry of F2 to Z and Rn is very different. So maybe if there's a way to combine these conjectures and find some algebraic way of proving this. Okay, so there are some relations between these conjectures. Now you can ask also, if you go back to communication complexity, you can ask, well, can we extend this to randomized or quantum protocols? So for example, you can ask, well, if you assume our matrix has low approximate rank, can we find an efficient randomized protocol? So basically, using the same techniques, you can always show that there is a large rectangle which is almost monochromatic. This still works. But I don't know of a way of bootstrapping this to get a protocol. So there are still some details to be worked out, so I don't know how to do it yet. And then finally some speculation, so sort of, so what I think that, if we want to get even more progress on the log-rank conjecture, then sort of we have to use the fact that the function is Boolean in a strong way. So really I think that this discrepancy technique really utilizes only the fact that, let's say, it's half the time plus one and half the, and it doesn't care about what happens in the other values. So that actually follows this conjecture. So really we should try and find stronger ways of utilizing the fact that this function is really Boolean. And sort of it seems that Euclidean geometry seems to play an important part, in particular in proving these discrepancy bounds, and it's not clear how to generalize this to finite fields. Okay, thank you. Any questions?
Thanks. Okay, so now is the time to ask questions.
Hi, this is Lassi Babai, and I wanted to ask how tight is this lineal and company lower bound on the slight discrepancy?
So, okay, so it is tight. Well, maybe up to a constant factor, because you think of the Hadamard matrix, n by n Hadamard matrix, it has rank n, and it has discrepancy 1 over root n. So for full rank matrices, it is tight. It might not be tight for low rank matrices, but for full, if you just think of the rank and you ignore the side, it is tight.
So if the rank is small, it's not that there is a better quantum communication protocol known. Like even not putting bounds on the approximate rank, but even if the rank is actually very small, or any kind of condition under which like a better quantum or a better randomized protocol is known.
Yes. Okay, that's a good question. So actually, so I had a work recently with Dima Gavinsky where we showed that if you have low rank and you want to prove, let's say, the log rank conjecture, then it actually suffices to give a randomized protocol. So if you have a randomized protocol, then you can use it to build a deterministic protocol, and you can even generalize this to low information cost. But for example, we don't know how to take a quantum protocol and the low rank property and convert it to a deterministic protocol. So this part we don't know how to do. But yeah, conceivably it might give you some benefit. Yeah, so we don't know.
I have a question, but it might take more time to answer. But since we have time, I don't know. Can you hear me?
Yes, I can hear you.
When you were explaining step 3, I think, of the proof, or the discrepancy, so where you were boosting this fraction of +1s that you found in your rectangles, you changed the distribution in order to do that. So you started with the uniform distribution, but then in the next step, you wanted an unbiased function, so you had to change the distribution, and then you obtain a rectangle in which the discrepancy according to the distribution, the bias according to the distribution was shifted in the way you wanted it to shift. You don't need to keep track of these distributions that change all the time, like it, so you get that the function is biased, but it's always for a different distribution inside the rectangle.
So actually what you get here, yeah. So let me know. Okay, what's going on here? Yes. So actually, what you get here is that every step you find the rectangle. So if you go here, so I'm starting with the basic assumption, the first assumption, that the function is biased on the current rectangle under the uniform distribution on this rectangle.
Okay, so I missed how you switched back to uniform. So can you show that? So because
yes. So you start by saying, well, so think we're in some rectangle and the average is some C. We choose a distribution that's going to be unbiased, and we're going to unbiased. We find a large rectangle, and you can show that on this rectangle. Think about it. Under mu, the function is unbiased, but on this rectangle under mu, it's now positively biased. So it must be that it has an even larger fraction of +1s and -1s than what it should have if it was random. And you can work out the details and see what you get. And this is the lower line is what you get at the end. There's actually different proof techniques that Salil Vadat, so I gave this talk in Banff, and Salil actually had a different proof technique which was actually nicer, that he avoided this amplification step by using the minimax principle. So actually, I uploaded a recent version of the paper to ECCC, which uses Salil's proof. So it's sort of somewhat simplified. So you don't have to keep track of these distributions as you go along.
Okay. Yeah, because it really seems like this is what you were doing, playing some kind of a game. Some player is choosing distribution, another is choosing a rectangle or something, and then you're making. Okay.
Yes. So that's way you can either prove it directly by finding these distributions, which is not very hard, or you don't do it and you just use minimax. There are two ways you can prove it, and they give you the same answer at the end.
Okay. Thank you.
So do we have any more questions?
I have a question, and I apologize if you just answered this question. We are having some technical difficulties. But I saw where you used the rank in the first and the third step, but where is the rank being used in the amplification step? Where's low rank helping you there?
It doesn't.
Oh, it doesn't. You don't need low rank.
No, you don't need. So we're using rank twice. We're using rank first to say that the discrepancy is large, and we're using rank at the end to say that you can stop some amplification when epsilon is small enough, when you're very, very biased.
Okay.
But inside the amplification step, you're not using the low rank property.
Okay. Thanks.
Hey, Shachar, can I ask a question?
Sure.
Do you have a conjectured improvement of the lineal result that would give you a stronger bound than the square root R?
No, so last year already asked, so if you just look at discrepancy, then that's a tight answer.
Right.
One of the roots of rank is tight.
But if I include something in addition to discrepancy, like size of matrix, because you keep changing the measures, so it might not help, right?
Yes, that's true. So I think what might be possible, but I have no clue how to do it, is somehow utilize the fact that you have very low rank in a very large matrix, and somehow do some type of Ramsey type arguments there, but because you have very large matrices. So this might give you something extra, but I don't know how to do it. So I don't have any specific conjecture.
And the fact that your matrices keep shrinking is not the problem. I mean,
no, because they don't shrink that much. So they still stay pretty big.
All right, R is quite small, right?
R is quite small, yeah. So everything here is only makes sense if R is at most like log squared n.
So in principle, one could try to guess a stronger version or some different version of this linear that might imply better upper bound.
You could guess, but I don't have a guess of what might give you a better bound.
But I mean, the other parts seem to be it's not the bottleneck. The other parts are not the bottleneck. Like,
yes, no, this is a bottleneck. This is definitely the bottleneck.
Thanks.
So, Shachar, in your conjecture, you ask, you have a matrix that has half of its zeros, and you ask a full zero submatrix that is large.
Yes.
Would it suffice to have a submatrix that is almost fully zero?
Yes. Well, if it is almost is 1 minus 1 over, let's say, R, then that's enough because you can use the same lemma, right? The same thing that
oh, that didn't depend on the plus.
No, it didn't.
On the Booleanness.
No, the same thing would work.
Mm-hmm.
Yeah, so if you're very close, then yes, that's enough.
Well, okay, so 1 minus 1 over R is enough, or 1 minus 1 over root R, or I mean, what?
No, 1 minus 1. I know. Well, this lemma works when it's 1 minus 1 over R. Let's see if I can go. I said, I'm in the wrong direction. Sorry. Yeah, that's like 1 minus 1 over R. So then, and it will be like almost all zeros. So you can ask if a function of 0 is 1 minus 1 over R, then the same thing would work. Same argument would work. Yeah. This is correct.
Maybe while there is a this expanded silence, I can insert a non-technical comment. The pronunciation of Lovett is an S at the end, not